Motion in our daily life can take many forms. The Diwali rocket executes translatory motion. Some more examples of translatory motion are the motion of a parachutist, a bullet fired into the air, and a football kicked into the air. The other type of motion we come across very frequently is rotatory motion. The rotating motion of the blades of a fan is an example of this type of motion. Other examples are the rotating motion of the blades of a mixer grinder and the rotation of the blades of a turbine. In these examples, the motion repeats itself after a certain fixed interval of time. Hence, this type of motion is called periodic motion. Periodic motion is exhibited by all the planets revolving around the Sun, since each planet has a fixed time interval for each revolution around the Sun. Periodic motion is also exhibited in other cases, such as the to and fro motion of a sewing machine needle and the movement of the piston of an engine. The to and fro motion of a body is called oscillatory motion. Let us consider a string fixed tightly between two walls. When the string is plucked and released, it executes to and fro motion. All oscillatory motions repeat themselves after regular intervals of time and hence are periodic motions. However, every periodic motion need not be an oscillatory motion. In the oscillatory motion of a body, there is a force that always directs the body towards the position, which is the position of zero displacement. This position is referred to the mean or rest position. This force is the restoring force. For example, in the spring shown here, which is fixed to a rigid support and the mass attached to the spring oscillates. The spring oscillates about the mean position. The motion of the bob of a simple pendulum is another example of oscillatory motion. In the simplest form of oscillatory motion, the restoring force on the body is proportional to its magnitude of displacement, but is opposite in direction to the displacement from the mean position. This type of motion is called simple harmonic motion. Simple harmonic motion is the to and fro motion of a body, where the force is always directed towards the mean position and is proportional to the displacement but in the opposite direction. Thus, the simple pendulum and the spring with vertical oscillations are executing simple harmonic oscillations. The oscillation of a boy on a swing is an example of simple harmonic motion. In practice, oscillating bodies come to rest at their rest position due to external forces which oppose the motion, called damping forces. The energy of the oscillating bodies dissipates due to the damping forces, and hence the oscillating bodies lose energy in the course of time. Hence, the boy swinging on the swing gradually comes to rest. To maintain the oscillations, the swing must be pushed by somebody such that the swing always reaches the same extreme positions. The person pushing the swing applies an external periodic force, which allows the swing to continue its oscillations in spite of the damping forces. Thus, understanding the concept of oscillatory motion helps to understand various physical phenomena. As you learned earlier, all oscillatory motions, like that exhibited by a pendulum, are periodic motions. The smallest regular fixed interval of time, after which the motion of a body in oscillatory motion repeats itself, is called the periodic time or time period, denoted by t. Time period t is measured in seconds. Consider the example of a simple pendulum that exhibits periodic motion. Now, allow the pendulum to oscillate freely and note the time taken, say, for 10 oscillations. Here, time period t will be equal to the total time taken for the given number of oscillations divided by the number of oscillations. If the pendulum takes 20 seconds for 10 oscillations, the time period of the simple pendulum will be equal to 20 divided by 10, which is equal to 2 seconds. Therefore, the time period of this simple pendulum is 2 seconds. What is the frequency of an oscillatory motion? The frequency of an oscillatory motion is the number of oscillations performed in a unit time, that is, 1 second. It is denoted by the letter n. In this case, the pendulum shown executes 10 oscillations in 20 seconds. That is, in 2 seconds, it executes 1 oscillation. Here, frequency n will be equal to the number of oscillations by the time taken, which on substitution gives the value 0.5. Therefore, frequency n is equal to the reciprocal of time period t. Frequency is measured in cycles per second, CBSE, or Hertz, and is denoted by the letters Hz. Named after the scientist Heinrich Rudolf Hertz. Now let us discuss the displacement of a body executing oscillatory motion. Consider the same example of the pendulum moving. When the pendulum moves away from the mean position O towards the extreme position, its displacement from the mean position increases. And when the pendulum returns towards O, the displacement from the mean position decreases. In oscillatory motion, all displacements are measured from the mean position. The displacement can be positive or negative after fixing the reference position. For example, if the same pendulum were to oscillate towards the left of the mean position O, its displacement can be taken as negative, considering the right side of the reference position as positive. The displacement variable in general can be understood as the variations in physical quantity with time in a broader sense when the variable involved oscillates. The varying electric current in an AC circuit and varying electric and magnetic fields in an electromagnetic wave can be considered as displacement variables. Since the displacement in periodic motion varies periodically with time, the displacement theta can be expressed as a periodic function of time, like f of t is equal to a cos omega t, where omega is the angular frequency measured in radians per second. The condition for the function f of t to be periodic is that if the argument of the function, which is omega t, is increased by integral multiples of 2 pi radians, the value of the function remains the same. Thus, a cos omega t plus 2n pi must be equal to a cos omega t, where n is any integer. In other words, the function is periodic with the time period t, when f of t plus t is equal to f of t, where the time period t is equal to 2 pi by omega. The function f of t is equal to a sine omega t is also a periodic function, which implies that a sine omega t plus 2n pi is equal to a sine omega t. A linear combination of two periodic functions is also periodic. For example, a periodic function can also be of the form of f of t is equal to a sine omega t plus b cos omega t, with a and b are constants. If the constant a is equal to d cos phi and the constant b is equal to d sine phi, where d and phi again are constants, then we can rewrite the function as f of t is equal to d cos phi sine omega t plus d sine phi cos omega t. Simplifying the expression using trigonometry, we get f of t is equal to d sine omega t plus phi. We are aware of the constants a and b. Hence, we need to express the new assumed constants d and phi in terms of the known constants a and b. Using trigonometry again, we get the constant d is equal to under root of a square plus b square, and the constant phi is equal to tan inverse b by a. We discussed a periodic function that is a combination.